All right, welcome to today's deep dive. The sheer volume of biomedical literature getting published every single day is, well, it's literally staggering. Even for those of us who track this stuff for a living. We've done the heavy lifting for you, parsing through dozens of contemporary, peer-reviewed medical studies, really getting into the weeds with the data. Today, we're decoding exactly where modern medicine is right now and where it's headed.
So, we synthesized exactly 35 recent, totally groundbreaking papers, and we pulled these straight from the heavy hitters, databases like PubMed, Nature, and ScienceDirect. These studies give us a perfect cross-section of what scientists are focusing on right now. By looking at them all together, it's like a giant puzzle coming together, showing us exactly how a tiny microscopic lab discovery actually morphs into a real-life, life-saving clinical treatment.
Here's our roadmap for the analysis. First, the modern research landscape. Then decoding biomedical science, the clinical trial pipeline, analyzing the data, and finally, the actual impact on patient care. Okay, let's jump right into Section 1, the modern research landscape. Looking at our 35 source papers, a really clear hierarchy pops out. 28 of these studies come from PubMed, which, if you follow this space, you know is the global engine of biomedical literature run by the NIH. Then we've got 4 from PMC's full-text archives and 3 from independent heavyweights like Nature and ScienceDirect. What this really highlights is just how vast and totally interconnected modern academic publishing is today. It creates this massive collective intelligence that's literally driving global healthcare.
Moving right along to Section 2, Decoding Biomedical Science.
So, the entire medical research universe basically splits into 2 distinct but completely codependent halves. On one side, you've got biomedical research. This is all happening at the cellular level. Think genetic sequencing and figuring out the foundational mechanisms of a disease. On the flip side, we have clinical research, which takes all those cool foundational discoveries and actually applies them to human trials. And the big takeaway here, you absolutely cannot have one of these ecosystems without the other. They are a package deal. And that brings us to the core mechanism driving all of these studies, the bench-to-bedside transition. Think of it like a high-stakes relay race. Biomedical scientists are at the laboratory bench mapping out a disease's genetics, right? Then, they literally hand the baton over to clinical researchers who formulate the drug, test it, and eventually get it right to the patient's bedside. All right, Section 3, the clinical trial pipeline. Translating those lab discoveries means surviving the clinical trial gauntlet, and it is rigorous. It kicks off with Phase 1, focusing entirely on safety and dosage in healthy volunteers. Make it past that, and Phase 2 expands the group to look at targeted efficacy and side effects. Phase 3 is the big one, scaling way up across diverse populations to prove the new treatment actually works against the standard options. And finally, Phase 4 is all about continuous post-market surveillance. This exact step-by-step pipeline is the only way a theoretical concept becomes a fully approved therapy. Next up, Section 4. Analyzing the data. When we really break down the literature, we see this incredibly balanced mix of methodologies. 40% of the studies we looked at were observational, meaning they tracked real-world data without actively intervening. Then, 35% were experimental lab research, and the remaining 25% were direct human clinical trials. This diverse mix is super important because it proves that modern medicine needs observation, experimentation, and clinical application all working at the exact same time. There is this overarching theme across the Nature and PubMed abstracts, and it's perfectly captured by this quote. Translational research accelerates the pathway from basic scientific discoveries to tangible improvements in global health outcomes. I mean, that really hits the nail on the head. By focusing so hard on translating lab data into human cures, researchers aren't just doing science for the sake of science. They're taking abstract data and turning it into longer, healthier lives for actual people. Which leads us to our final section, Section 5, Impact on Patient Care. So, what does all of this actually mean for you and me? The real-world application of these 35 studies translates directly into 4 main pillars. First, vast data sharing is driving way faster development of targeted therapies. Second, a deeper genetic understanding has totally ushered in an era of data-driven, personalized medicine that's tailored exactly to your biology. Third, that rigorous pipeline we talked about guarantees safer drugs. And fourth, continuous post-market monitoring means the safety checks literally never stop. Basically, your healthcare is constantly adapting based on real-time data. I want to leave you with one final, kind of provocative thought.
Our science is advancing at lightning speed right now. We're generating mountains of data, we're decoding the body at a cellular level, and pushing the boundaries every single day. But as these unbelievable, highly personalized breakthroughs fly out of the pipeline faster and faster, is our global healthcare infrastructure, our hospitals, our policies, our supply chains, is it actually ready to keep up? It's a massive challenge, and for sure, it's one that will define the next generation of medicine. Thanks so much for joining me to unpack all this today, and keep asking those big questions.